Okay, we're looking at problem 12-22 as an example, and let's read it. It says a particle moving along a straight line is subject to a deceleration a of minus 2v cubed meters per second, where v is also in meters per second. Acceleration meters per second squared, velocity in meters per second. If it has a velocity of v equal 8 meters per second and a position of s equal 10 meters when t equals 0, determine its velocity and position when t equal 4. So if we're going to go with the idea of this state diagram, so let's first of all say clearly two states, a state 0 and a state 1. And what distinguishes them, then this is t equals 0 and this is a t equal 4. And we are given some additional data that says velocity of 8 and position of 10. V equals 8, S equals 10. Okay, and we want to determine its velocity and position when t equals 4. So v equals, want to know it, s equals, want to know it. And what's going to transition between these two states is a equal minus 2v cubed. A equals minus 2v, not cubed, yes, minus 2v cubed. Okay? So looking at this, time is important, so we are going to want to deal with time in these equations, but we're starting off with a of v, and they're really, looking at our equation sheet, clearly we're going to be working in this area of the equation sheet. We could work with a, v, and t, or we could deal with a, v, and s because we have a of v. We could package a of v here. We could package a of v here. The author's solution went with the ads equal vdv form. We'll look at that in just a second, but let's briefly look at going the other choice, a is equal to dv dt, by writing a equal dv by dt. And we have a as a function of v, so we would rearrange this and package this as dt is equal to dv over a, bringing a to the other side, but a is equal to minus 2v cubed. And then we can put integral signs around both sides, and t is going to go from 0 to some indeterminate t, and at t equals 0, v is 8, so we'll be integrating between 8 and some indeterminate v. Now, this is very doable. We can integrate this thing. The only maybe interesting issue is v is cubic in the denominator, and that's slightly more complicated than what we get when we go with the ads equal vdv form. So I'm not going to carry this one any further, but it's a perfectly viable alternative. And what this left-hand side would give us is t is equal, and then this would give us a function of v. Basically a function of v to the minus 2 power dot 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 is the kind of thing that we would get. Then we can proceed ahead by inverting this and getting v of t, and then integrate again to get position. Let's look at how the author did it. Either one is a perfectly fine alternative. The author's process may be mathematically simpler. So we're starting off with a ds equal v dv. We'll bring the a to this side. So we'll have an integral ds over v dv over 2v cubed. And one of those v's is going to cancel. So our function is going to be dv over the minus 2v squared. We've lost a v, makes the integration a little easier, maybe makes the rest of the math a little bit easier. Now, being very careful, our beginning ds will be the starting ds, which is 10. That was given as part of the data. Our upper limit on s is just an indeterminate s. Now, the v that corresponds to s equal 10, and both of these correspond to t equals 0, was the value of 8 meters per second, integrating to an upper limit of an indeterminate v. And so when we integrate this left-hand side, we're going to get an s minus 10. And when we integrate the right-hand side, we're going to get a 1 over v to the first power type term and plugging in our limits. It will give us this right hand side, and we have S is a function of V. Now what we do is do enough algebra to isolate V by itself as a function of S when we put everything else together. That algebra leads to V is 8 over 16s minus 159. So what we have is V of S at this point. And so now we need to proceed further. We need to come up with S as a function of time. So the next step, since we have a function involving S, V, and we want to bring in time, the equation that does that for us is our very first equation that involves S, V, and time. So, using dV equal ds dt, but doing a little bit of scrambling. We give us dt on the left-hand side, sorry about that, and ds over V of S. So we'll have the integral dt on the left-hand side integrating between a lower limit of 0, upper limit of t, and then we will have ds divided by the V of S that we got from the previous page, this integral, integrating between limits of 10 and S. This is going to give us a quantity t minus 0. When we integrate this side, we'll get an S squared type term when we integrate this side, and we can see that the 8 got moved over. So both sides have been multiplied by 8. And so we get that 8 times t equal to this quadratic. If we wanted to, I suppose we could try to solve for S of t algebraically. We don't really need to do that. What we can do is simply plug in t equal 4 right here and solve for the value of S that makes that true. So we do that. We plug in t equal 4. We solve this quadratic equation, and we're going to get two answers, and they didn't tell us what the two answers from this quadratic were. It says choose the root, which would be the solution of the quadratic, that is greater than 10 meters per second, so that is presuming that we were proceeding forward, and we get 11.94 meters. Now that we know S at t equal 4, we have an equation for V of S, which we derive back here. So we can plug in that very same S right here and solve for the value of V and come up with 0.25 meters per second. And that would be the answer to that problem.